This is Group 12. Our topic is DJ, enabling high-density multi-tenancy for cloud gaming servers with dynamic cost-benefit GPU loading balancing. The authors of this paper are Sergio, David, Alec, and Roger, and the presenters today are Chiyu-Lin, Kasima Bulan, and Jayashi Pridivi. This is Chiyu-Lin. We can start now. Before talking about our topic, let's have a short look for some keywords that we will mention in this paper. The first one is frame rate, the frequency at which consecutive images called frames appear on the display, which is also known as frames per second. That's a moving scene we saw in our normal life. It usually applies to film and video cameras, computer graphics. And the second one is rendering. Rendering is a process of generating an image from a model by means of a software program. It is also used to describe the process of calculating effects in a video editing file to produce final video output. A rendered image can be understood in terms of a number of visible features. For instance, shading is how the color and brightness of a surface varies with lighting. There are a lot like reflection, transparency, so on and so forth. Motivation. According to the paper, the authors mentioned there are some major problems within cloud gaming, which are latency, bandwidth, and multi-tenancy. Latency and bandwidth have been talked in other resources. It's here. So the main problem the authors want to solve is multi-tenancy. Talking about multi-tenancy, the SAM isolation and virtualization support that has served traditional host service well would surface for multi-tenant gaming also. However, cloud gaming multi-tenancy is challenging and distinct from traditional data center multi-tenancy. The reason is that games exhibit three unique properties, which are GPU-centric workload, continuous deadlines, adjustable visual quality. But what caused multi-tenancy being a problem of cloud gaming? It's GPU processing. For gaming, GPU processing is a bottleneck resource. One avenue to multi-tenancy is to create a static partitions of the GPU for each application instance. Because we have to manipulate multi-tenancies who want what they are going to experience always has the highest quality. It means we should take care of their satisfactory of the gaming experience and also the availability. Commercial GPU visualization solutions from Citrix and VMware already provide this capability. However, this leads to very poor server density for two reasons. First, users come and go, making static partitions unaccommodating. Second, a game scene complexity and corresponding GPU load can change dramatically over time. For example, a user in a virtual environment may view a simple room at one moment, and then navigate to view a complex garden environment in the next moment. Unfortunately, a static partition must allocate conservatively for peak load, since poor frame rate during some scenes is unsatisfactory. This means during any non-peak load, which occur frequently, GPU cores sit idle. This waste leads to inefficient operations on the part of the service providers. So the mission to the topic is to find a balance between availability and resource wasting. Then, how to deal with presenting these two kinds of scenes. These two scenes are just like what we mentioned in the last slide. A simple scene and a complex scene. If a server chooses to statically provision for the worst case of all players visiting complex scenes all the time, which means allocating for peak load, wasted resources and over-provisioning will be significant. Naively, running multiple tenants concurrently on the server can pose grave shortcomings. A load generated by one instance can squeeze out another instance, resulting in missed deadlines, low or erratic frame rates, and an unplayable experience. Even the load generated by a single instance exhibits significant temporal variability due to scene complexity. Simple scenes with a few basic objects and no effects, such as figure A, render much faster than complex scenes such as figure B. Players can encounter both simple and complex scenes within a brief window of a single session. These are why the authors built DJ to address these shortcomings. They care about 2 points, which are cost in terms of GPU time and benefit in terms of visual quality. Utility is the basis for DJ's three main functions which enable it to maximize aggregate visual quality, and we will talk about it later. Now, let's see if this is an important problem. Of course, yes. How to provide client satisfaction in visual quality, being stable and available all the time. Obviously, every player wants to play a game smoothly. Due to different objects leading different using in GPU level, we would fail by allocating fixed resources to all things, so we must give in the most resource of GPU to our client, but it causes GPU idle. If the GPU is scalable, then it would not be a big problem. However, the problem is how fast we are able to adjust the amount of GPU that we are going to allocate to our client. I'm going to extend the previous slide by adding this additional question. Is there any other issues? Yes. We talked about the problem of scaling is how fast we are able to adjust the amount of GPU that we are going to allocate to our client. In briefly, the main thing this paper has done is to estimate the utility. We now know how much resource we are going to allocate, right? But the problem of how fast we can give wasn't mentioned. If the speed of scaling isn't that fast, a potential problem would be delay, and delay causes bad user experiences. Moreover, it's about money. If I have a gaming server, I should know how much resources are going to be scaled could lead to the minimum cost. And I want to make sure the cost is always the lowest it is supposed to be. Also, it should satisfy all my customers and be stable. That's why I think there are some issues not being included in this paper. We need to think about the whole process to deal with the problem. Did the authors motivate convincingly this problem? This is relevant to the previous slide I added. They do care about the cost of GPU time and how to estimate the distribution of GPU resources to clients. They want to find a solution to address the shortcomings of creating static partitions of the GPU for each application instance. But there are more problems related to this issue, just like I said in the previous slide. Is the importance theoretical, practical, or both? It's both. In theoretical, it is important. If the amount of users increased, we can calculate how much loss the server would encounter. In practical, the authors have applied DJ on real productions, and we know it does help. Are there any solutions out there for this problem? There is a solution from NVIDIA in 2018. If there is an advanced GPU virtualization, it would be a solution to dynamically scaling. According to developer.nvidia, Kubernetes on NVIDIA GPUs enables enterprises to scale up training and inference deployment to multi-cloud GPU clusters seamlessly. It lets you automate the deployment, maintenance, scheduling, and operation of multiple GPU-accelerated application containers across clusters of nodes. In short, we can dynamically scale GPU to nodes very fast by buying GPU clusters. We know that GPU was not able to be split without GPU virtualization in the past. In order to improve the performance, we can only add one GPU at one time, but we still don't know how much GPU we should provide to our services, and the speed to respond to demand is slow. Kubernetes on NVIDIA GPU actively monitors our operation and allocates resources we need. Due to the availability of GPU virtualization, allocation of GPU resources are accelerated. The utility of GPU clusters are optimized by monitoring the operation. You can learn more in the video of 2018 Kubernetes, a keynote at the GPU Technology Conference. And this part starts at 1 hour 11 minutes and 13 seconds. What are the similarities and differences between this work and existing solutions? The similarities is to solve the using of GPU resources in the cloud. The differences are, first, DJ uses pre-calculation. They estimate their utility, and NVIDIA uses scaling. Second, the difficulty of parallelization in gaming and machine learning are different. In machine learning, they just added trend model copy into computation cluster, and DJ is stateful. Then NVIDIA is stateless. We should pass the current situation to it when we add new resources to make sure the continuous of our game. These two solutions do help when we are talking about the problem of lacking GPU resources. Only when we are in the implementation, there are something inside and outside the structure should be adjusted due to issues of network or others.
Okay. Now, before getting into the architectural implementation details of DJ, I would like to mention some terms and components that are used in this paper. The first and primary thing that we're going to see is the notion of utility. Like Shiyu already discussed, measuring the cost in terms of GPU time and benefit in terms of visual quality is the prime measure that is taken here in this paper. So the second thing is the frame time or the frame rate. So the most acceptable frame rate for any cloud gaming to provide usable performance is 30 frames per second. The inverse of it is 33 ms per frame. So if you see the GIF image over here, we have two animations, one for 15 FPS and 30 FPS. We see it more carefully. 30 FPS is more fluid for a gaming experience. So anything below this value is strictly not acceptable for cloud gaming. So the next thing we're going to talk about is the rendering settings. Almost all games provide this capability to change or alter them. So developers offer these settings because end user machines can vary greatly in capacity. That is, a user with a powerful machine can enable more advanced settings, whereas a user with a not so powerful machine can tone down these settings to maintain the acceptable frame rate. So in DJ, the users have used some preset settings, rendering settings, such as low, medium, and high. And in the right-hand side, we see a screenshot of the rendering setting options that are provided in this game, Table 3. So here we're going to be discussing about the two main questions that DJ aims to answer. First one is, what rendering settings are feasible? And second question is, among the feasible, which setting would be the best? But the problem here is, a rendering setting that is feasible for one scene might be too expensive for the other. And the second problem is, when we term one rendering setting as the best, it might not be the best for a next scene. So these are the two questions that DJ aims to answer. So finally, we're going to be talking about the three main functions in the DJ architecture. First one is the utility profiling. Next is the utility estimation, and finally, we're going to be talking about utility maximization. Okay. So let us talk about the different components in each of the functions described, in the previous slide. So the first thing is utility profiling, and the first component that we are going to be discussing is SSIM, which is structural similarity score. So it is a standard criteria used to quantify the loss and video quality between an original image and a distorted version of the same image. So the original image can be represented as F star, and the distorted image can be represented as F. The main thing to note is that the SSIM values take, the range between 0 and 1. So in the next example that we see over here, we have three images. The first one is the original image, which has an SSIM value of 1. The two other versions of the same image has different SSIM scores. we notice that the value of SSIM is less for a more distorted image. That is, lower the value of SSIM score, the lower is the accuracy of the image compared to the original one. Okay. So next component we are going to be discussing is deterministic instance concurrent execution, which is nothing but DICE. So we know that for calculating SSIM score, we need an S star frame and an S frame. The question is, how do we obtain these frames? So this is where DICE comes into play. The idea is to run two instances, namely a master and slave of the same game concurrently. The instances will only differ in the rendering settings. That is, the initial state, user input, everything will be the same except for the rendering settings. The master will generate F star frames and the slave will produce F frames. So using this, SSIM scores can be easily calculated. The next component we are going to be discussing is AOL, which is Active Objects List. It is just a list of objects that are going to be used by the game to build a particular frame. So values that are received from this list are going to be given as input to the next component, which is dprof. So dprof is the most central component of utility profiling. So basically, a new scene will contain different graphical objects. So by calculating cost in terms of GPU to build each object, we can calculate the total cost to build the total frame. So dprof is a component that measures cost and performs the mapping of costs to different graphical objects. And dprof does it by using statistical regression models. Okay, the next function is utility estimation. The first component in utility estimation is TOL, which is potential objects list. As the name suggests, this is the list of objects that are likely to be encountered by the player within a short span of time. This list can be used to alter the rendering settings of future scenes. The next one is DEST. DEST is the central component of utility estimation. So DEST estimates the cost-to-benefit ratio of upcoming scenes by giving different rendering settings. So basically, DEST receives TOL updates. That is the objects that are going to be encountered in the future. They get the TOL updates from the game and estimates the cost-to-benefit ratio with respect to different rendering settings. So once DEST estimates all these values, the values are given to DOPT, which is the next component for utility maximization. Now, the function of DOPT is to take utility computed by DEST and compute the most effective rendering settings that can be propagated to all the sessions in the server. So now that we've learned all the components, let us look at the architecture of DJ. So we have online profiling and utility maximization. The first thing is profiling. We see we have DIs over here, which starts a master and slave instance and calculate the values of F star and S. Using this, we can calculate the SSIM scores of each frame. And then there is an AOL list, which is active objects list. So all these list values are given to dprof, where the cost is mapped to different objects using the regression models. Now these values are given to DEST. Now DEST calculates the values of future frames, that are built in different rendering settings. Next, the value of DEST is given as input to DOPT, which calculates the best rendering setting possible, which can be propagated to different sessions in the server. So DEST is going to be using TOL, which is potential objects list, to estimate the values of future frames. And DOPT is going to be calculating the rendering setting that can be propagated to the different sessions inside the server. Now, we are going to be talking about each of these functions in detail. The first thing is building game object profiles. So for a session F and rendering setting R in a frame F, the costs and benefits are calculated using the equation that is provided in this slide. So basically, W are the weights of cost and benefits, where J is the unique object ID of the game object present. So using these equations, we first there is a game object profile. And the next thing we do is DICE, which is deterministic instant concurrence execution. Now, DIs requires to run the master and slave concurrently for every session. So to do so, we have to choose to run these two masters and slaves, in a non-traffic time. So the authors suggest that we run masters and slaves during new game onboarding where the user rate is less, or during times when the load is less on the server. So the third thing that we're going to be discussing is object filtering. So basically, we can filter the number of objects that we provide from AOL to DPROC because we don't want the DPROC to be overloaded with too many objects. So there are two types of filtering that is done. The first is based on vertex count. So basically, the number of vertices in a 3D object is counted. The more the number of vertices, the most important the object is going to be. So any object that has very low or lesser than the threshold values of vertex is going to be pruned. The next type of filtering is based on the weights of the costs and benefits. So the second level of filtering is needed because vertex count filtering alone might not be able to prune too many objects. So this way we are reducing the load on DTOR. The next thing we are going to be discussing is the future utility estimation. So basically, DEST uses the weights from DPROC to forecast the upcoming costs and benefits. So DEST uses POL list, which are nothing but objects that are that are likely to be visible in a short amount of time. So basically, we calculate the costs and benefits, which are C prime and D prime values, shown in this equation in this slide. So where I is the same number, J is the unique ID of the game, and S is the current session value with the rendering setting R. So the final one is utility maximization. Here, DOP has too many questions to be answered. The first thing that we are going to be talking about is how, DOP would be able to decide the quality for each session. So basically, sometimes DOP might have to downgrade or upgrade the rendering settings for sessions based on new users entering or dropping. And also DOP should make sure that this change in visual quality does not disrupt the gaming experience for users. So the first question is initial assignment. How do we assign the rendering settings to all the sessions initially? The main idea is to assign the minimal possible rendering settings to all the sessions, and then if any residual time frame is left, we can improve the rendering setting. So we are doing this by using the marginal utility value, which is calculated using the equation that is given over here. So the next one that we are going to be talking about is how DOP does a graceful change during normal operation. So basically, we don't want the rendering settings to go from the highest quality to the lowest quality abruptly. By doing this, users might notice an abrupt change in, their gaming. This is not what we want. So to avoid this, DJ has provided a mechanism where only one level of rendering setting can be gone higher or lower such that the user does not notice fluctuation in the rendering settings. So the next things that we have are two major conditions, which is warning and critical. Now, DOP triggers a warning condition if the total frame time is between 33 milliseconds and 40 milliseconds. And it triggers a critical condition if the total frame time is more than 40 ms. So during these conditions, DOP has to take charge to, lesser the value of rendering settings such that the frame time, is below 33 milliseconds. The third thing that we are going to be discussing is managing session churn. So over here, when new sessions are, added to the server, we can provide it the highest possible rendering setting based on the residual time frame. Or if the residual time is going to be very less, the only thing that is going to be possible is providing it the lowest possible rendering setting. If there is no residual time frame left, we cannot accommodate this new session. So there comes this failure condition called admission control failure. The authors have left it to future work to accommodate distributed systems for cloud gaming. Now, to answer the question, is this a significant contribution? I would say it is, as most cases that we looked at spoke about latency and bandwidth problems in cloud gaming. But this paper gave us some good knowledge about how to accommodate several users in a single server, that is multi-tenancy. Therefore, I think this idea put forth by the authors is also original for single server environments. So here, to implement DJ, authors have modified the source code of Doom 3 and Fable 3, the two games, to include components like dproc, dice, DSC, and doff and all. So basically, authors have extended Doom 3 and Fable 3 to invoke a DJ API, which requires data based on the type of operation. So that is in profiling mode, data structures to provide AOL list and to calculate, different F star and F frames for calculating the SSIN scores. All such data is taken. And in the optimization mode, POL values, that is, future object values, all such data is, given to the API to calculate the DEST and DOF values. Next, coming to the evaluation, we see this graph over here, which shows the predicted and average values of regression models estimation accuracy by DJ at 4 different locations in the game. We see that all the predicted and average values are almost close. So the prediction that has made and shown proved by the authors are quite accurate. And the next thing is system overload. Now, since DJ is designed to operate on live instances in both profiling and optimization modes, it is important that the overhead of running these two, does not affect the entire gaming, environment. So we see that the profiling overhead is as minimal as 0.6 ms, and the optimization overhead is only 2.8 ms. And the main thing to note over here is all these overheads are CPU costs and not CPU costs. So this way the game performance is not affected at all. Now coming to multi-tenancy and scene complexity test. Test for multi-tenancy shows that 4 players are joining one by one. Now for both games, it is shown that DJ provides the most optimal rendering settings in all cases. And also over here for scene complexity, the effectiveness of DJ is promising because it provides the most optimal rendering settings if you see over here in this graph. Now the last thing that we are going to see is the high load responsiveness. Now test for high load responsiveness shows that when aggregate load hits the 40 ms mark at frame 131, DJ acts quickly to drop this frame time, at frame 135. This is done by downgrading the rendering settings from high to low. So, in my opinion, the authors have provided enough theoretical analysis and prototype implementation and simulations when necessary. But when we get to this question, if they have demonstrated it multiple times or not, I would say no, because they have only demonstrated the system in 2 games, which is Doom 3 and Fable 3. It also has limitations because, both these games are written for Windows platform and Windows hypervisor do not support high-performance GPU virtualization. Whereas other hypervisors such as VMware and Citrix do not have this limitation. As a result, the games rely on host OS and GPU device drivers, core scheduling, and memory management mechanisms only. The second limitation is DJ only supports running one game type, at a time. So the future work can include concepts like load balancing across, different servers and, hosting different games on a particular server and so on. So basically, though the authors have provided a great solution for multi-tenancy, I think there is scope for, future work which would help understand distributed systems and load balancing better.
About the last point, actually, this is the first time for me to learn deep about gaming, especially in the cloud. When I searched related information of this topic, I was so surprised how advanced cloud is. Though the implementation of different types of services in the cloud are different because of their structures, we still can learn from those successful models and try to improve the solution to suit our problems. As a previous slide talking about NVIDIA's solution for machine learning, that is really amazing. I'm sure that I will go deeper in this area in the future and keep an eye on something new here.